As we saw in the last video, one of our general principles for the relationship between stored potential energy and work looks like this. We say that the change in potential energy is equal to the negative work done. And again, we reference our spring. This is the energy stored in the spring. This is the work done by the spring. And so we see an opposite relationship here. If we take the general idea that work is a force that's applied and it's an object is moved through a given distance, and this is a general statement, not specifically to a spring, but maybe to like the gravitational field, because the force is constant in a gravitational field. We can see that the change in the potential energy is equal to, I forgot the negative. The opposite of the force times the displacement, the change in position. But this here, when you use the deltas, this means an average, or over the total amount. It's not an instantaneous change. In order to do an instantaneous change, we need to take our deltas, our changes here and our changes here, and make them infinitely small so that we can see the instantaneous change. And so to do that, we use the little d's. These mean instantaneous. And so, if I switch from a average change to an instantaneous change, I can say that the instantaneous change in the potential energy is equal to negative the force times the dx. And what I like about this is going to give me a very specific relationship. So if I rearrange it a little bit, I can say that the force is equal to the negative du dx. Now, what does this mean for us? Well, this is our derivative notation. So this is the derivative of the potential energy function with respect to the position. So if we consider an object that's moving along a position, maybe it's moving there and back, or it's just moving there, as the position changes, maybe the potential energy changes. That's what we have here. And what this means, remember this is derivative notation, so this means that the force is equal to the negative slope of an u versus x graph. This is a big idea. Okay, this is a big idea. So if you happen to be given a potential energy versus position graph, like this one over here, we can actually glean a whole bunch of information. And one of the important points is that the force on it is the negative slope at any point on here. But let's talk about what this thing over here means. This is a weird looking function. First of all, this is the potential energy, and here's the position. So if you think about the roller coaster in the last one, as the roller coaster moved this direction, the potential energy changed based upon its height. And we can get a sense that this might be analogous to that. So here, when our position is our object is at position 0, its potential energy is 6. Then at position 1, 5, 0, 3, 1, and then 4, and then beyond position 5 it stays at 4. So we get questions like, okay, this is the potential energy function, right? How can I understand it a little bit better? Well, the first thing I want to do is say, do we know the total energy? Because if we know the total energy, then we can actually get some more information. So let's say, for example, that our total energy, okay, what if our total energy was equal to 5 joules? So this is our total energy. Well, one of the things about this that's cool is when we're talking about mechanical energy, we're only talking about either the kinetic energy or the potential energy is our total mechanical energy. So in this situation, our energy total has to be equal to the potential energy plus the kinetic energy. And what this does is it allows us to infer some information on this graph based upon this. So one of the things I said was at position 1, the potential energy value was 5, and then here the total energy is 5. And so I can ask this question: what is the speed of the particle when it's at position 1? Okay, well, let's check it out. At position 1, I know that the total energy has to be equal to the potential energy plus the kinetic energy. Let's plug in what we know. What's the total energy? Well, it's 5. It's 5 the whole time. The potential energy at position 1 is also 5. So what does that mean about the kinetic energy? Well, it means the kinetic energy is equal to 0. Therefore, the speed of the particle is equal to 0. That's actually a great conclusion, because it goes one step further in this, because we ask the follow-up question: can our object move to the left of position 1? We know the potential energy function kind of looks like it could, but can it really, given a total energy of 5 joules? Let's check. If I go, let's say, to the left of position 1, let's say I end up with 6 joules of energy. So if my total is 5, my potential energy is 6 plus the kinetic. This gives me a strange result that I don't like. It says that, oh, my kinetic energy must be equal to -1. And that is not an actual thing, because kinetic energy can never be negative. If kinetic energy is equal to 1/2 mv squared, m can never be negative, and you can't square a number and get a negative number. So in a real situation, kinetic energy can't be negative. Therefore, given the constraint that our total energy is 5 joules, our object can never move to the left of x1. So that's an interesting result. What that also means, okay, what this also means is something else that's important. Is given this point right here, if our object was moving to the left, for example, if our object was moving to the left, what would happen is it moved from x2 to x1. Well, as it moved from x2 to x1, down here at x2, let's check the situation there. Okay. Same idea here. The total amount of energy is still 5. At x2, the potential energy is 0. Therefore, the kinetic energy is equal to 5, which means it's moving fast. Now, I told you it's moving to the left, and that's fine. We just know it's moving fast. So at x2, it's moving fast and moving left. We know up here, it's not moving at all. So what has to happen as it moves from x2 to x1? It's clearly slowing down. Now, this is what I like about this, because when it gets to this point up here, we know it's stopped. But what direction is the force on it, is the question. What direction is the force? Well, let's look at what our rule says here. The force is equal to the negative slope of a potential energy versus position graph. We have a potential energy versus position graph. So, what do I notice about the slope right here? Is the slope positive or negative? The slope of this line is negative, which means the force is positive, which means it's pushing the object to the right. Okay, that makes sense, because we know from x2 to x1 the object is moving left but slowing down. If it's moving left and slowing down, that means the velocity is left but the acceleration and force are to the right. That makes sense. And when it gets to this point right here, when it gets to position x1, it stopped, but the force is to the right, which means it's going to start moving back to the right. So we call this point right here a turning point. Our object moves to the left, gets to the turning point, stops, turns around, moves right. What's going to happen when it gets past, well, first of all, can it get to x5? And if it gets to x5, what's going to happen when it keeps going past it? So if we check x5, at x5, let's work it out again. We say that the total energy is equal to the U plus the K, potential plus kinetic. My total energy is still 5. What's the potential energy? It's 4. So therefore, the kinetic energy must be equal to 1. No problem. What that means is that it gets to this point right here, has some kinetic energy, which means it's still moving. But notice my potential energy function right here. Once it gets to this point right here, this is flat. Well, what does that mean for our particle? Well, if the force is the negative slope, what do you notice about the slope of this section right here? The slope is equal to 0, therefore the force is equal to 0, which means it's not going to have any force on it at all, which means if there's no force, there's no acceleration, an object in motion stays in motion. So if it can get to x5, which it can given this amount of energy, it's going to hit here, and it's going to keep going and never come back. What if instead of my total energy being 5, what if my total energy was, let's say, 3? Okay? What if my total energy was 3? This situation would be a little bit different. Okay? This situation would be a little bit different. Okay? If my total energy was 3, we're going to see a different situation here. So let's say my object is at x2 again, okay, and it's moving. It could be moving left or right. How far could it get to the left and the right of x2? That's a great question. Well, when I look at this, I know that the total energy can't be more than 3 joules, or the total energy is always 3 joules. And so, could my object get all the way to x3? I think it could. So let's see how that looks. So at x2, our situation stays the same. We now only have 3 joules of total energy. At x2 it's 0. So our kinetic energy is 3 joules, which means it can be here, and it can move left, and it can move right, and it's moving fast. But let's talk about x3. Our total energy is 3, but look at our potential energy. It's also 3. which means our object stops. So it can get here, but it stops. But what I like about this, is our object can get right to here, and it can stop. But what do you notice about this point right here? It's our local maximum, and so if you put a tangent line on there, you would see that tangent line is horizontal, which means that the slope, so the force equals 0. So if it got to here, according to this, it could get right here, but it would stop right here. And it's in what we call unstable equilibrium, because if it got any kind of nudge to the right, we then have a force to the right, and it would go even farther and faster. Or if we got any kind of nudge to the left, it would move to the left and also have a force to the left, which means we would go farther, faster. So this is an unstable equilibrium right there. Okay, it's an unstable equilibrium. And then we wonder, how far to the left could it get? Well, if it stops when it gets to this total energy height, which means it could get to here, so it could never get to x1, it could only get to this because x1 has total energy of 5.